Okay, good afternoon. So for today, as I promised, I'm going to have the recording. It is definitely for our uh, preparations for the final exam. Okay, for the students, as we already done all the lectures classes, and now this is, I guess, that just giving you a generative idea how actually it's look like your final exam questions. And I do this recording because of there are a few also student asked about the exam final exam questions, and then I do promise that I'm going to have this recording at least for 1 hour. Where we're going to do the review for all the chapters will be in the final exam. And yeah, now I'm sharing my screen. Later, once I've done with this, I'm going to put into the announcement tab by the My Times. You can find here the recording and also your coursework. And I'm truly apologize. I can't to upload your coursework on last Tuesday because of we are still waiting for the Bravo section. And Bravo section not yet done the submission. I mean, not the submission. It's not done yet. The marking. So hopefully that we can still giving a time by today, and we can upload all the course mark for all the student from all the sections, so that we were going to have. So for today, I'm going to put all the recording link in this announcement tab. Okay, and also the in course mark for you in the announcement tab. You can take a look and keep checking on the announcement tab. All right. So as I mentioned before, we going to have a exam, final exam, and the thing is, I also already uploaded a three set of revision review questions. So on these three sets of review questions, you will find each of a set is following the chapters. So the first set of review questions, this one. Okay, this is a chapter instruction set. And you will find the next set, which is set 2. This is for next chapter about the multi-core processing. And we understand basically for the computer architectures, especially for the processors, we have a single processors and the multi-core processors. But before this chapter, if you still remember, we have a parallel um, um, computer processors. However, that it is having kind of like related study to the multi-core processing. So I'm going to wrap up that parallel processing towards to this set, which is multi-core processing. And the last set for our revision, if you take a look, we also have a set 3. And this set 3 is regarding on the computer architecture trends. Okay, this is for computer architecture trends. I think I miss here. It's going to be the trend. Yeah. So we have 3 set overall. All right. There are a student which is asking me about the format of our final exam. For both, which is final exam set 1, and also for those who are um, probably need to resit for the final exam because you've been barred, or might be you failed for this first set, so we have a second set for the receipt paper. So for the both, which is final exam set 1 and receipt paper, which is final exam set 2, will be having a similar format. We have actually we have a part A in here. So this part A basically is a 50 marks. And we also have part B. We have a part B also 50 marks. I need to repeat again because there are students asking me about this one. And then for the part A, is all actually a short question. So when I say it's all the short question, you're going to be have a 2 mark, you're going to be have a 4 mark, going to be a 6 mark, kind of. And then part B is all, we have a 3 questions. Okay, we have a question 1, we have a question 2, we have a question 3. And question 1, all of this is basically is a case study. This is a type of a case study. And each of it for this 25 marks. This is for 25 marks. This is 25 marks. And you can choose actually only two. Let's say, for example, you choose question 1 and question 2. So we're going to pause this 25 marks with a question 2, 25 marks. You have a 50. So you can total up with the part A how much you get, and there will be a total overall. So consider the overall of this final exam. Actually, we have 100 marks. So from these 100 marks, we just only taken over 40%. Okay, so we know your midterm test is 30%, and then you also have your group assignment 30%. So there actually 60% in total. So you need to plus with this 40%, then you get 100% for your all assessments. All right. So okay, let me moving on the first set. Okay, revision set 1. All right, so this is a revision set 1. How many of questions in total? We have about 15 questions. Okay, so if we look at back to this chapter instruction set, it's in a general we touch about the architecture, computer architecture, which is we have completely understood about the complex instruction set and also reduced instruction set. So that is the earlier of that computer architectures evaluations. And we also need to know what is the instruction set and the features of instruction sets for the complex instruction and reduced instruction. And after that, we also learned about the what we call typical of instruction set has been understood by the computer machines. And we learned, okay, what is the opcodes, and we need to understand their language, which is they used to have like assembly language for the computer machine. And this assembly language, I guess, apparently similar like our language, that instead that we try to interpret the kind of binary number as the instruction set. So then when we have to know about the assembly language, which is in the chapter 3, there you are, we know exactly the typical instruction set, which is it's following the discussion table. And I introduced to you to the discussion table that time. So a part of this chapter is that introduced to the student about complex instruction set, reduced instruction set, the features, we also learn about very typical of instruction set, as like in question number 2. And we also touch about how actually the process of a machine cycle. So we understand that if you still remember during my lecture, I mentioned about what you call it. There's a YouTube. Okay, there's a YouTube talk about machine cycle, where that how that the program or instruction set is being fetched in the code. Then after that, it will be executed to be stored or to be released. So that also will be inside this chapter. And we do exercise and practice about how this machine cycle it works, if you still remember. So overall, this is the questions, okay, about this chapter. And I do mention, which is you just need to practice and exercise our revision set, these 3 sets, okay. One of it is a this set, all right. And then I do not saying that you no need to use the slides, but what I prepared for you for this revision set basically is considered is a fully material to support you to do the to do the preparations for your final exam. So that's what I can say. So if you just study this revision set and tutorial 10 and 11 for supporting document for you, it's a good enough for you to I guess be prepared, okay, 110% for our final exam. Okay, so let's we go for the revision set 1. And before I go for the how that machine cycle works and that's exercise, let me see certain of a general informations. I mean that kind of knowledge in the computer architectures. Basically, we have kind of two type of the computer architecture. But anyhow, before we go for that, we need to know what is instruction set, and we understand that instruction set basically is the computer program, is a piece of a computer program. Okay, and then it's giving semantically the functions. What are the functions? We understand is for the fetch, for the decode, for execute, store, and load. Any of the instructions, which is it will be processed between that our main memory towards to the our processors to be executed. I mean the CPU units. So we understand that that is there is something, there is value, there is a data, and then this data basically is like one of a piece of a program to fetch, program to decode, program that to execute, to store, and to load. So they will definitely might possible have a question about the instruction set. Might possible, I say. So I'm giving you the sample of answer directly for each of questions. And what will be the mean of a category of instruction set? We understand that we have very typical instruction set definitely is following that machine cycle. We have a data transfer, we have for the ALU instructions, we have control units and input and output units. So this is a typical of the category instruction. And I also put there in the bracket example of the instructions. So we found these all instructions in the be familiar with the assembly language, right? We found this in the assembly language. However, that we used to have this instruction while that we were given by the description table. So we understand that the computer machine going to fetch, going to decode, execute, store, or load of the instructions following these instructions. So they can be move instruction, can be a jump instruction, can be store instruction, can be the arithmetic instructions like, for example, multiplication or addition, So this kind of it. And we be introduced to the description table. So I'm going to talk about that later. And then we know that we have a complexity, we can call that as a CICS, a complex instruction set, this is the first computer architectures in the world. And then this computer architectures instruction set, I just said that in the very short term, ISA, I stand for instruction set architectures. They will be developed by the Intel's company. We have x86 architecture. We have ARM architectures. So this is all the architectures, the oldest version, which is started in 1970s. We cover about this trend in the last chapter in this module. So after that, we also have RISC, which is reduced instruction set. And we need to know the differences between these two computer architecture in terms of the instruction set. So I also put in here what is the differences. Okay, that's in the point form in here. We understand that the previous complexity of the computer architectures are quite like difficult to we understand and to be programmed. That one is a type of CICS. So it's required a large set of instructions and then quite complex operation. Anyhow, that after this development, they do to have another architectures and manufacturers of RISC, and then a bit small, and then each of the instructions was set will be breaking to the small portion, and then we can find this one normally for the I believe current of computer architecture set instructions what we have right now in the world. So CICS is a before RISC. So they will have chapter about the data manipulation for this chapter. But the main point here, how to differentiate between CI and RI. So we know CI for the complex, definitely is a large or huge of instruction set. And then definitely when you have a large or huge of an instruction set, you're going to have like kind of complexity to the computer machine to execute all this large. And the data definitely like going to have not efficient to be executed. So we understand that there is the most of I guess that challenge, when during this time. So there's a thing, and we have a RIC, which is that large of or huge of instruction set will be breaking down to the smaller, and then it will be solve a certain of a problem, such as like the we understand operation that including kind of many of parallelism can be solved by this instruction set. So you need to know the differences between complex instruction and reduced instruction. And we've been introduced by the description table, and I mentioned about instruction set. They only have kind of a three main of components. First of all is the opcode, second is the operand, and address mode. So if you still remember our slide here, okay, this is basically the slide that I've been used before. All right, then I talk about this thing. What is the opcode and operand? And in the operand, they will have two types of the component, which is the locations for the memory. We call it as a register, and then bit pattern. So the bit pattern, most of it is considered like one of the value. It can be the value of the memory address in the PC, or maybe in the AC, any of the registers in the cache memory. And a bit pattern also can be like the value of the instruction that need to be executed or to be transferred or to be fetched. So we learned about this one, so no need for me to remind you on this. All right, and then description table. And for this description table, okay, we understand it definitely showing how that computer understand the instructions, okay, need to be processed in between our CPU units, processors units, and memory units. So we have opcode, it stands for operations code. I say like this is like a secret code or Morse code, computer understand that the most significant digit on your left basically is the opcode, and then there's a operand. Operand basically like the symbols, okay, to show or to be referred. Then we have each of the operand have their own functionality. So we were giving you this language description table during your final exam. You will find that in your question paper at the end of the page. We enclose there, and then you can refer to and find out which of the opcode and operand will be used, okay, basically based on the question we've given to you. So if you still remember what I was saying during the lectures, the most important, basically you need to know the number of operands, the number of opcode in here, okay, until the end. And I promise you that I'm not going to have all opcode and opcode exclusive rotations and jumps, but we're definitely going to have the questions for the one that I circle here. Okay, at either number 5, number 6 will be in your final exam. All right, so recall back this instruction set, okay, for opcode number 1, okay, and we have a load. Opcode number 2 also we have a load. The difference between these two, for opcode number 1, we're going to take the memory cell value. It means the address of your memory location. And then for number 2, it's going to load actually directly to the value on the XY. And we understand all of these instruction set have a 4-bit, 1, 2, 3, 4 bits. And then the first bit in here will be the opcode. let's say for example in here, the second bit will be your register, which is current instructions register value, which is, this is the current location, the new location. Whatever happened in this bit, let's say this is the bit number 0, this is bit number 1, this is bit number 2, this is number 3. So what will be happen in the bit number 2 and 3 going to be stored in the this register, bit number 1 here, following whatever that the opcode be represented. So we understand that. And we also kind of like knowing that we have opcode number 3 for the store. So we understand that if you need just copy all this description into your answers later in your final exam. If let's say we have 3 is an opcode 0, 1, 2. So we know that this is opcode number 3. We refer to opcode number 3 in here, and 0 here basically is the register value. So you will say that, oh, number 3 is the function is to store the bit pattern form in register R. So we know R here is a 0. Oh, so whatever value in the register 0, we're going to store, okay, which is where's the address? We look at that is a X and Y. So we know X and Y, this is the X, this is a Y. So this is our register, and this is our opcode. So basically we're going to have a question for this, okay, instruction set. And all right, I want to take a look on the example of a question. What we'll be having in the final exam. Basically, it's like question number 1, question number 2, question number 3, So it can be any. It can be any. It just for you, what you need to know. All right, you read slowly and carefully the question when this question in your final exam. And for your information, this question will be in part A. Part A, short questions. How many marks? Most probably actually 10 marks for this question. So this is compulsory for the student to answer this question because it is in the part A. Part A, compulsory, you need to answer all. Part B, you need to choose only 2 out of 3 questions. So we look at to the question number 1 in here. The most important, okay, to score these questions, you read slowly and carefully the question and then take a look where that the starting point, the starting address that machine cycle will be from. And then they need to be processed. So in this case is 0, 0. So as same as in your practice tutorial classes, okay, we're giving you the address. Definitely this is your memory address, and then each memory address will pointing to the data inside that memory. So we understand this, right? For example, in the memory cell address 03, the content or the value inside this memory 03, which is 04. In here, we have a memory, like for example, this is your memory cell. Okay, this is 00, this is 01, this is 02, this is 03. So in here, right, 00 will be a value 21. 01 is a 0B. And then we have a 03, 04. So we have here 04 value and so on. So that is what does it means. So, all right. Okay, give me 1 minute for this one. And read carefully the questions. Normally we're going to ask you what will be the bit pattern for that particular register. So once you have or receive this question, we understand we're going to start with 00 address. Okay, what we required you in your final exam, you need to draw what we call a few of a table, but basically just make it one table in here. What we need in this table, we only need your program counter, okay, incremental of a program counter, and then your current register IR, Okay, and then the description in here. Only that. So this is the table that we're looking for your final exam. Okay, if you want to score 10 marks total, I believe everybody can do that. All right, look at to the example of a question just now, and this is the sample of answer. I have a copy. This is from the question. Okay, if you take a look back, this is the address. This is the content. Right. So this is the table that I required you to do. This is the table. And I need to have a program counter column. I need to have the increment number of increment program counter columns, the current register column, and the description table. I mean, the description from the description table. So we understand that if you have a 4-bit of address like this is a 4-bit, this is also 4-bit. We look at to the question. This is the question, yeah. So we have a 1, 2, we have 3 and 4. So we have 4-bit. All is a 4-bit. So when we have a 4-bit, that program counter will be in have an increment towards to 2. Okay, so here we're going to start with 0 because question asking you from 0. And how many of increment? Number of increment? Definitely 2 because of 4-bit. So we have a 0, 0. We're going to take a look, start with a 0, 0. And then increment 2 times. So we're going to combine these two together. 0 and 0, 1. All right, so we're going to take 21 and 0B here. And we're going to pass and bring to our current register, current instruction register. So that's what we have here, 21, 0B. And as usual, we're going to read the description table and we look at to opcode number 2. So we understand in the opcode number 2, description table, basically is load. Okay, take a look on this. This is load. And it is very straightforward. This opcode number 2 directly take the bit pattern X and Y. So when we look at to the question just now, okay, we have a 0B. So if we want to translate this to the description table, we know we just copy from the description table. You write down in your final exam, load the R. What is the R? R is the second value in your current register, number 1. Load register 1 because this value is 1, just replacing in here 1. With a bit pattern, what will be the bit pattern? That is the 3rd and 4th bit pattern. Okay, so the current one, the bit pattern is a 0B. So bit pattern 0B. And I always inform my student during my tutorial, once you've been given by this type of question, directly you're going to create this table and another table, which is this table. Okay, this table, same. What you need to have, which is you just directly put in here the address. Address number 0, address number 1, 2, 3, 4, 5, and 6. So the current of address, this question, 0, 0, they were definitely 2-bit. But the new table for the new current register, we're going to have only 1 bit here. See, this is all 1 bit. 4, 5, 6, 7, depends on the questions. Okay, this is the current. You will see that this is the current, this is the new. This is new table. So we understand that in this, new table here, we only have a 1 bit. Look at that, 1 bit, 1 bit, 1 bit, 1 bit, 1 bit. So for the new table, you create the address and then you leave it alone, which is the content for each of the address, okay, empty. So now when you have this one, let's say the first instruction, opcode 2 is a load register 1. So you know register 1, you refer to register 1. And then you need to map your value of the bit pattern. Register 1, it's set, and you load directly bit pattern 0B. Okay, directly you're going to load the bit pattern 0B, this one. So you directly push to the 01, number 1, register 1, this one. So that's why you will see this is F a 0B. So next, you're going to continue 02 and then push to the next program counter. So our accumulator right now holding 02. Okay, the counter. So it's they will have an increment 2 times. Okay, so 02 will be with a 03. So we look at 02 in the what they call original of a value here. This one is 02. And then with a 03, combine these two. So we combine these two, we're going to take the value content in this address 02 and address 03, 1404. So that's why you can see we push 1404 in this IR. Okay, and then back to the register, description table, you see opcode number 1. Okay, and in the description table, opcode number 1 also load, which is we're referring to this opcode number 1, and that is also load. Load register R with bit pattern found in memory cell X and Y. So you copy that, and in your final exam, you copy that. Sorry, it's loading, still loading. I don't know. It's okay. So you just copy from your description table, say load register. So what is the value of register? Always the second digit in this in this current IR. So for register 4. Okay. And then with bit pattern found in memory cell. This one, okay, number 2, direct tick the bit pattern, but this one found in register memory 04. Where did I get the 04 from here? Okay, the third digit and the fourth digit. Okay, 04. So it said you need to load register 4. So you need to stand by register 4. Where is the new location for register 4? This. In the here, here. Register 4. So the thing is, they said you need to load any of a value. It's found in the 04. So you look at to the original of the address in here. You see 04 here. This 04 is a is a C0. So that's why we're going to include in 04 here C0. Same goes like this. Okay. Then continue. And then push this one down here. 04. Increment 2 times 04 and 05. So we're going to take 04 address value combined with 05. Yeah. And the value will be C0 and 00. So that's why in the current register here we have a C000. So we have a C000 here. Okay. And we understand in the description table, if let's say this is the operand, we understand that it's going to be stopped. So that's why we stop. Back to the question, it has a question, what bit pattern will be in register 4 and what bit pattern in register 1. So this is the bit pattern, register 1 0B, register 4 is a C0. Okay, so for, I'm deleting question number C, all right, because of I want to simplifying this. We're going to try again, okay, the next question in this instruction set. As usual, read the questions slowly and carefully and then see when they're going to begin. This question begin to 00. Is there any possibility in your final exam the program counter going to start at 01? Maybe, but that's why I said you need to be careful and then check where it's going to start. This program counter will start maybe here, or maybe here. I do not know, but you can check on the question where they start. So if it's 00, so we understand it's going to start in here. Okay, let's take a look on this question. Copy paste back the address. This is the current address. I just put this is the old address. And then this is the new address here. This is a new address. So all address always have a 4-bit pattern. And then here, 4 bits address and then instruction set. And then for the new, always we just use single 1 bit here. 1 digit, 0, 1, 2, 3, 4, 5. So What is the step to answer this question? Once you get the question, detect where they're going to start, and after that, draw the table. First table, which is include the PC counter, program counter, incremented counter or number of increment, and then current register and opcode or the description. And then create another new table, which is your new memory location. Just try to have like two columns. One is for the memory address, one for the contents here. And then you can start with a 0, 1, 2, 3, 4, 5, always like 5, 6 kind of that value we put inside in our questions. Okay, for this question, we start with a 0, 0. So basic counter will start with 0, 0. Because it's a 4-bit pattern, the increment number will be 2 times. So we have a 0, 0 and 0, 1. Increment will be 2 in here. So this one will be combined together. Okay, this one will be combined together. Then you will get 1, 0 and 0, 2 will be in your current register. So we refer opcode number 1. It's actually said number 1, load. Load any of a bit pattern found in the memory. So we write down, okay, load the register. So what is the value of register? Is a 0 here. So that's why the value here is a 0. And then where is the memory address? The bit pattern, the value we need to take off in 02. So look at the old of addresses. 02 is in here. So we're going to take value of 24. So that's why in our the new of addresses, now we have a 24 in register 0. So this is actually instruction set for the first one for this. And this is showing that how that computer machine or your CPU execute this instruction 1002. And we're going to move on to the next of a process. We bring forward a 02, increment 2 times. So we have a 02 memory value with combination 03. So that's why we understand that from the old address, the machine computer will take over this value. And 2404 will be in the current register. Replace this and we have the current offer instruction. So from the registration table, we understand 2 will be also load. And then 4 will be registered. So number 2 direct take the bit pattern 04. So we know 4 in here. Doesn't matter you want to put 04 or 4, it's still correct. So we know where we're going to load this value in the register 4. Go to your new of cell. Okay, find the number 4 here and then load the value of 4 in the content in this memory address number 4. So we understand that this is actually execute the second of a operation, which is the instruction set is 2404. And we keep doing that until at the end, until that computer machine is held. So 04 go down here, increment 2 times, that's why it becomes 06. And then we're going to do the combinations address set of instruction will take these 2 of address B4 and 08. That's what we have here in the current of register B408. And when we take a look on the questions, discard first. When we take a look on the questions, we have just now the questions of B, right? This is the opcode. So look at today's description table, B. B, basically the instructions, if you look at to this one, give me 1 minute or 1 second. All right. The B instruction basically is, in this case, here, this opcode, and this is for jump operand. So, but don't worry, in our final exam, we do not have questions on jump instruction. We do not have. This is just for exercise today. Okay, when the jump, we just copy the question. Okay, jump to the instruction memory cell at address. Where is the address? if you look at the description table, okay, it's a jump to instruction located in the memory set address XY, XY. So in this example, XY definitely a value of 08. Okay, we can see here, this is the value 08. This is actually the value of X and Y. Okay, but they said you're going to jump this instruction if you found, okay, the bit pattern in the R register, R in here is a 4. So it may be referred to the new of the register memory location 4. We're going to see this value. All right, is that is same in the register 0. Because where do we get this register 0? We get this register 0 basically from the description table. So where is register 0? Basically from your new, not from your old. Old 0, 0. From your new is a 0 here, only 1 bit. So you need to compare this value and this value. Is it same? If not same, no need to jump. So in this case, it's not same. 24 compared to the 4. Definitely no. So you no need to jump. I just presume, then I put it in here. So no jump. I put that no jump. Right? And then what is the next? Okay, we're going to bring 06 down here. And then the 06, we're going to refer to the old of our register. The 06 will be combined, all right, with 07 here. So C00 the value and 07 value for this memory address 07 is a 00. So we combine the bit pattern or the value in this memory 0607 is actually C00. So we stop. So as simple as that basically is the instruction set, machine cycle in these questions and this chapter. Basically, for me, okay, if you're able to, let me see revision set. All right, I also include in here this instruction question number 14. I include this if you're possible to execute this. So definitely that you are possible to answer my question in final exam. But make sure, first of all, you have first table. The first table, it's include the columns of PC counter, incremented number of a PC counter, CIR, current of instructions register, and description. And then after that, I need to have a new table for the new address. Okay, so that is for this chapter. And what will be other things in this chapter? Okay, I said to you, we have 3 questions in the final exam in part B. All right, in the part B, we have a 3 question. And all of these questions in the part B will be what we call case study type of questions. So they will have many questions, but that question will related to the case study. So like for example, question 1, they will have a case study about set instruction. Question 2 will be have a case study about multi-core processing. And then question 3 will be about computer architecture trends. So that's why I come with all in the package into this set of revision. So there will be definitely, let's say, for example, question 1 is there's a case about the company who wanted to change the current of computer architecture to the new one and the new one. But they will have question like, for example, okay, what is actually the features of instruction set in this architecture? And that architecture, for example, can be the complex instruction set architecture. Or might be that architecture will be the reduced instruction set architecture. So that's why if you look at to this revision question, I have compiled all the necessary for you, okay? And it just need for you to know that we have kind of this question in your case study. Some of our students asked me that, Miss, this question set questions basically is like conceptual question. Yeah. If I giving you a case study, seem like I giving you the whole bunch of the real of a final questions, final exam questions. So it's unfair. So if I giving in the conceptual of this type question, then you will see, oh, what is basically instruction set? Instruction set will be the bunch of a program. It is what we call possible the bunch of a program for the machine cycle. Okay, it's having a few of categories like A, B, C, D, and E in number 2, and then obviously the first of computer architectures have instruction set they call complex instruction and reduce of instruction. What is a complex instruction? Oh, complex instruction, it has a kind of huge of numbers of instruction set, which is it's a difficult to understand and then to be designed by the programmer. So definitely they have a complex operation, which is it will be affected to the process of executions, and then it's going to be take like multiple clocks cycle to execute. However, that is been improved towards to the RSC, reduced instruction set. And then what will be the reduced instruction set? The name also reduced. It's going to reduce the number of instruction one time to be executed, and then they can execute like typically in the single clock instead of that multi-clock. And then I also giving you an example on that. So once you have that, you need to know about that how the computer machine cycles will be operate, which is the example exercise we do that just now. And yeah, I also include in the question number 5 and question number 6 the characteristic of a complex instruction and reduced instructions. As you can see in here, they are more on like point form. Okay, let's say for example we take a look on this one. What question number 5? What is actually C? Sorry, what's actually is a CISC here processor. Okay, it said support many instruction, and then including specialized one of complex operation. We understand if support all many instruction one time to be executed, definitely you will be have a delay. And then you want to load many instruction, and then processors need to distribute and then isolate each of instruction, execute one by one, and then they will definitely have a queue. So we understand that there will be definitely combinations of not only one single instruction, can be more instruction, and then the size will be inconsistent. So it's dynamic size. So this is what we said. They will be quite thoroughly difficult for the programmer to do that. So we know that this is one of the keywords, and then even there's a lot of flexibility, but because of it's a complex, so they're going to be typically take a time to finish or complete. And we understand that in the CIS complex instruction set, they're using multiple clock to execute. Nevertheless, that for the reduced instruction is opposites. So understand that they're focusing on the simplify the operation of instruction because of they want to have an optimize of performance. So this is what we have currently in our computer machine. And then the memory access limit specific instructions only. And then high instruction throughput because it's a small of instruction to be breaking down from the bigger instruction from the CI. And then simple. Okay, simple. However, that the counter will be higher or increased. That's it. They will definitely have question, which is you need to know what is the immediate instruction value, the address type. What is the immediate address? What is a direct address? What indirect address? It is in here. Okay, so I also putting another more question about that. I said differentiate immediate address and direct address. So we know this is an example of a value. If you apply immediate value, this is a direct value. So what is the difference? If you can see here, the difference, which is this is a value which is have a hashtag. This is there's no hashtag in front of that digit. Basically, this is specified direct value. So they take directly like a load opcode number 2 just now, directly take the value. But if actually we talk about direct address, which is like a load opcode number 1 just now in description table. So this is a difference between these two. And they have also questions about that our instruction set, which is what the features and then the challenge. So you can see that there is a question, which is I said here the challenge. Okay, the challenge. Okay, if you implement that instruction set computer architecture. Okay, so it can be many various. You can have a hardware complexity. You can have a performance optimization and a power consumption. Definitely, this is also become issue right now, and also memory. Okay, and maybe you're not very familiar with E. Is actually we talk about backward compatibility. What does it mean, backward compatibility? We understand that every 2 years we want to have a new of processors. So how the current processor that the company or the manufacturer trying to update the version. Okay, maybe I can give an example like it's involved with the older version formats. And then for the new format, how they go on to adding the new features. So that is basically the backward compatibility. The actual issue on compatibility. However, that I did talk about this one during my tutorial when we have a compatibility issue. So still, they can do improvement, and then they can adding certain of new features. For example, multi-thread processor and SMP processor. If there are kind of the challenges or consider, we call that the weaknesses or disadvantages. So the new version, when we talk about the backward compatibility, they will update, okay, and then they try to overcome the problem. So we have many things, especially for the current computer trends. It's need to be equipped with a facility to ensure the process of transaction for the real time, and also AI and security will be kept up. So this is backward compatibility. What else for this one? Yeah, I also mentioned what are specific implementation techniques if you want to optimize or improve the current of instruction set, because current technology also using RISC. Okay, so RISC is used to have a pipeline, parallel, superscale architectures, branch predictions like the switching, vector instructions. So this is an example of a techniques they used to ensure that there's no having an issue on in terms of the backward compatibilities. And you can take a look the rest. I think that I need to basically take a break, maybe 2 minutes, then we go to the set 2. All right, I will go to the set revision 2, and set revision 2 is related to the chapter multi-core, and also related to the parallel processing, that chapter. So for multi-core, we understand that for the processor, we have a single processor in the first place. Then they have an improvement and shifted to the multi-core processor, which is multi-processors. So that's why I put in there as a multi-core processing as the header of distribution set. And how many of a question we have in here? Yeah, only 10, but if you look at that, there are a lot basically for each of a question. This is more towards to like the transition from the single processor to the multi-core processor or multi processors. But before that, we need to ensure that we understand the terms of a multi-programming, multi-threads, and also multi-core. So when we talk about multi-programming, it means that there are more than one program can be executed one time or in the same time. If we talk about multi-thread, there are many threads can be executed, okay, in one single cycle time or might be in one time, okay. And then we talk about multi-core. It means they are gonna be have. It's gonna have more than one processor, okay. Can execute many programs, many threads in one time. So there's a thing. But little bit okay generative idea about this thing. We look at that each of particular processes definitely has a different of what we call features. So you need to know what is single core processor features, what will be the multi-core processors features, what actually type of multi-core processors. So then I guess that is a safe for you to answer the questions because we have a lot of questions regarding on this set number 2. Okay, first question, what is a single core? And we know when it says single, definitely only one processor with one CPU. So it has dedicated CPU, okay, from one single processor. And after that, what about the thread? If let's say this single core going to process or going to execute, the thread will be single also. Only one thread can be executed one time. Okay, and then what kind of normally the performance is will be involved. So they're going to use ILP, which is obviously different with ours right now. What we're having right now is using instruction level parallelisms. Same goes like very like old versions of RISC. And then what's the problem in the single core processor? Okay, make it bigger a little bit. Okay, that's A and B. I put in that limited ability to improve performance and then inefficient in multitasking because it's single. Okay, one by one, so they can't to do the multitasking. When they can't to do multitasking, obviously they can't to have, execute any of instruction if let's say in the real time sharing. Definitely no. So that is the issue in the single core. After we have a single core processor, then there you are, we have multi-core processor. So when we have multi-core processor, there you are, we're going to have like the terms, we found the terms of multi-programming and also multi-thread. Okay, so they call the name of this term is multi-core, definitely is more than one or more than single core. So they're going to have a more than one processor, the processor unit, PU, and each of processor have more than one CPU. So independently, it's work, but it's work together parallelly. Okay, simultaneous. It seems like if I draw in here, okay, this is a single processor before. Single processor, this is the processor, PU, and then this is the CPU. Okay. And then if you have a thread here, we have a thread here, we have a thread here. This is all need to be executed by the CPU. So of course, this is traffic jam here. But when we have the what we call foundation, the first of foundations of our RISC, and then the instruction set can be executed one time, even though a lot. I mean that more than one. So we have a multi-core. Let's say here we have a one processor. Okay. And then we have many of CPU, more than one CPU in here, more than one CPU. But each of the CPU have their own multi-thread. Thread 1, thread 2, thread 3. So they have many thread. And it's independently work together. However, for all of this, okay, thread, the CPU and from this, originally first processor, they are sharing the memory. So the memory sharing. Okay, this is memory sharing mechanisms. So this is the first multi-core processor. Then there you are. We have a new technology of a processor. We have they copy all of this. All right. We have P1, we have a P2, we have a P3 in here. All right, similar like that. But the thing is, they can share everything in here, the bus, everything. And imagine they have many CPU in here. There are no more dedicated pipeline for each of a thread. If let's say there's something busy in here, this is free, this is free. This can actually overtake this task from this CPU, even it's come from a different processor. So I mean, we understand they work together, simultaneous and parallel. No more dedicated pipeline like this. Okay. So this is a multi-core processor. Anyhow, that we understand in a multi-core processor, there are evolutions, okay, like an Intel series, as I mentioned during my lecture. Okay, this is the comparisons of a single core and multi-core. Processor unit only one. Multi-core have a more than one. Performance limited clock speed. This one parallel, as I draw just now. Power efficiency, of course, this is less. This is more because more processor. This is multitasking, time sharing. Here, parallel can do execution. Software dependency, this is less, this is more. I mean, this is not dependent. It is more towards to the independent. And each of that, it has their own of a software utilities. So we can conclude this is, you can have a question about this single core and multi-core. If I'm not mistaken, is in the part A. Okay, next question. Main advantage. What are the main advantage? What are the main advantage of multi-core processor? If you have a multi-core processor, which is all of actually from these features, all of from these features, what is advantage? Of course, you know that it can improve the performance. This is by logic. In my final exam question, okay, we do not have a definitely this is absolutely answered. No, it's as long as it's relevant, we accepted your answer. Okay, so what is the advantage if you have more than one processor? Definitely, you can improve performance, the power saving, and you have the task can be distributed, okay, and then it will be multitasking. Scalability will be wider or broader. So this is all by logic. If you use a different of words or term, okay, but we understand that the meaning is falling into the same meaning, so we still accepted your your answer and we give you the marks. Okay. There are the question which is why many technologies right now using multiprocessing architecture. Why? This is also very I think a very general question. Okay, it's a bonus for you. This question itself, if it's a final exam. We understand if you adapt the multiprocessor architecture, nowadays offered users expectations or demands all on the real-time transactions. This is a computer's trends right now, and then the demand in terms of various of different platform, and also the cost in terms of the energy saving and the cost of a buy and purchase. So that will be the why. Okay, many technologies nowadays using multiprocessing. You want to have a real-time transaction can be executed, okay, completely, and you want to save your time and also the cost. That's why they are used to have this technology. Simple. This is very simple question, and I guess everybody can think of about that. Next question, three-type multiprocessing. Okay, this is we learn from what we call our lecture class. We have a SMP, stand for symmetrics multiprocessing. We also have asymmetrics. Asymmetric is opposite to symmetric, and we have distributed multiprocessing. So I always like highlighting about symmetrics processing because this is what we refer to currently in our technology. Symmetrics, they are sharing. Okay, they are sharing all the general of main memory, and then the we call the threads It can be executed in any of the processes you need in that particular of a multi-core. Each core can execute others core threads, okay, independently because it's symmetric, okay. But actually, when we look at to the access on the each of cache memory, they cannot access it. But asymmetric, they can access it. So this is same goes like the issue if I draw in here. Oh, I have here. Okay, I have here. All right, in here, this is the case. Asymmetric, if you look at to this case, they have their own of memory, although they're sharing the memory in here. But each of this memory from the different processor, you see, this is processor 1, this is processor 2, this is processor 3, and so on, so on. Each of that is a same goes like the first or the new of a multi-core processor. Each of that core, okay, they're not sharing. Each is a memory, but the main memory, yes. This one, each core do their own threads, and then the thread actually divided to the. They're using an algorithm to divide the threads. Which thread can be executed by the processor 1, and then which other thread will be executed to the next other processor 2, processor 3, and so on. But this is not happen in the what we call other of a multi-core processor. So you can see this is different comparing to the asymmetrics. If asymmetrics, okay, I scroll up in here. This is asymmetric. Okay, they are actually sharing. Okay, if something the thread here cannot be done, this thread can pass to here, and also can pass to here as long as in this processor of the CPU, okay, and processor CPU in this processor is empty, they can pass, they can swap. But of course, they have like for example, in this case, they call that master and slave processor. They will have mechanisms, okay, switching mechanism and predictions mechanism in this case. Another one type of multi-core, which is distributed multiprocessor. If you look at to this one, I'm giving you this one is hyper of thread is the best super skill of processor in multi-core processing. Look at to in here, okay, they can share every single things. And then the difference between this and asymmetric, little bit, they require complex of programming. I did mention this in my tutorial, the differences, especially that if you look at to the this one with data center, okay, data center unit in here, when we want to talk about computational in terms of a basic computational in the AI and the basic computational that in the ALU units are holding on, they're totally different. Computational in the AI advanced, for example, how you to compute based on the algorithm the programmer perform, all right, they will have a formula for the pixels and they have a lot of methods such as like regressions techniques. So the ones the normal of ALU unit cannot make it. What they need, as in here, all right, they need ASIC. Okay, this is I talk about in my class. Okay, my tutorial class. ASIC is advanced of components to do that calculation. Instead that you have of course your CPU has been advanced, and then there are combinations, these heterogeneous of components, CPU and GPU, but still, okay, they can't to execute kind of advanced of calculation, computational for the real-time techniques and also AI. So they need you have an ASIC. So if you come back to these processor types, okay, set 2, this is the thing. So they will have kind of specific algorithms, which is they're going to distribute the task, which this is for the CPU, this is for the GPU, and this is for the ASIC. So this is a quite like considered like high end of a processor types of. So there's a 3 type of multi-core, and then I have a question about the load balancing. All right. I also have a question about the load balancing. What is the load balancing? So we understand that when we have a multi-programming and multi-threads, each of that CPU, GPU, okay, they need to execute and given the task equally, okay, to ensure that they're going to perform maximum of the performance, and they are possible to avoid or reduce the bottleneck of a traffic in terms of instruction set. You want to fetch, you want to decode, or you want to execute. So that's why they have a load balancing. Who's going to do this load balancing? Normally ASIC components. Okay, and yeah, I will have a question about like question number 8. We do to talk about parallelisms and partitioning. And then, yeah, this is also important table for you. Okay, let's make it bigger. All right, here. This is summary, okay, about that techniques in multi-core. Definitely we have challenges. Definitely we're going to have challenges to equip the computer processors and then trying to enhance the computer processors. And then the techniques they use, this is the thing. First of all, dynamic task scheduling. So you need to know what is a dynamic task scheduling. What is task partitioning? What is the load balancing? What is processor affinity? What is distributed load balancing? So how to solve if let's say there's a problem in the load balancing, and how you're going to sustain the mechanism of the partitioning, for example. So in our slide, we talk about the solution. This is the problem. This is the solution. So for example, that load balancing, what is the solution? It's about the switching of the partitioning or switching of a task, a thread. Let's say processor 1 busy, then the CPU and GPU cannot finishing the job, so they can pass to the next processor and next CPU. So that one actually is like switching, right? Switching order. So we have kind of a solution in our slide, lecture slide. What is, you need to know also what is the Messi protocol, what is Snoopy protocol. So that 3 protocol, okay, will be also possible as in your answer too. And what else? I have here, like for example, power management problem. So what is the solution? Scalability, what is the solution? Memory bottleneck, what's the solution? Complex programming, what's the solution? So please read this carefully. So I'm going to take a break for 2 or 3 minutes. Then I continue a third set, the final set, which is related to computer architecture trends. All right, now I'm going to continue the last set for your exam preparation. Set 3, it's related to the the final chapter of this module, computer architecture trends. When we talk about the trends, we keep to, you need to focus on the hardware and the software, right? The hardware and software, because of, we have questions about this too. And then if you still remember, for these computer architecture trends, we talk about the current technology. So the current technology basically following a trends of the applications. Okay, I refer to this slide. Okay, we have a question about this too. Trends. When we talk about the trend, is the how the evolutions of the computer architecture following the computer technology. So when there are new technology, definitely our computer architecture will be obsolete. Thus, that the design of the computer architecture for the current or maybe in before, it should be follow technology trends. What are the technologies? Like, for example, AI technologies. For example, we have a cloud computing. Last time we don't have cloud computing, and even last time, we have a different of a platform. We can't to communicate if we are not in the same platform of the operating system. So this kind of technology. So I'm going to refer to the Moore's law, and then there's Moore's law that we revise about this angle. Okay, this is the graph, and then if you look at to this graph, wait. So we have this is you see the size of all the scales of that increments of need, the need, okay, and processor, and then this is the year, okay, x-axis and y-axis in here, and then the most important, which is this straight line graph, and another one straight line graph in here. I did mention about this one. However, that Moore's law say that trend of computer architecture is following on in terms of that processor. Definitely, this is hardware, energy and operations, and memory. So we understand about that. We have many of our ICs, and transistors, all that from the bigger size to become to the small size. And then this is what Moore said, that 2-time increment within this period. For processor, 2 times. For energy, 1 time. For memory is 2 time. But we understand that this is not possible. And then actually this is only 1 time. I mentioned this one in the class, right? This is only half. And this is only 1 time. Because of it's the rapid of changes of technology, basically for our programmer, for our designer, they can't keep up very fast. Okay, it's very fast, so they cannot keep up. What we have actually, this is the line of the initiations of our previous of manufacturing company. However, that's good. It's a quite higher. Okay, in terms of that what we have right now for the processor is a higher. However, that in terms of memory, this is the issue. Okay, still slow. Our memory productions and then the design still slow. So when it is slow, they cannot keep up together with the processors. It's going to create the memory wall. So for the memory wall, we do discuss about why we have this memory wall. Okay, we do to have this one discussions. I hope that the collector also mentioned about this one. However, that the generated kind of issue, which is like for example, same like this graph. Okay, and then we have an issue in terms of the memory. If you look at this, is the memory of line of our memory productivities. Okay, and then after that still it's an inconsistent, and then they need to have more improvement, far enough. Okay, because the capacity of a memory, okay, compared to the what we have right now, especially used to say this technology is referring to the real time of system demands, and also for the AI demands. So these two is become more challenges. Anyhow, okay, this one I discard, and then we go to the side question. What will be questions in your final exam? Okay, take a look on this set revision. How many of a question? Total we have here 13 questions. All will be out in your final exam. And if you look at that, I emphasizing this. Okay, I emphasizing about the Moore laws. You can see that you need to do have a discussion about how the impact of that technology trends towards to the computer architecture, especially what we can see most highlighted. Three main component, which is processes, and then energy and the operations, and lastly, memory. So you need to have discussion about this. All right. And then they say, what are the trend technology that lead to these implications of changes in the CAO computer architecture? So you just mentioned about these three things: processor, about that the cost and power consumption, and the memory. I did mention this one in my lecture and also my practical. So revise back on that. And then I also having question. The example of answer here. You can read carefully. In terms of the trend, we understand that the performance for the particular architecture. So there is a difference, if you have that multi-core processor with different of architectures. So definitely the performance of course will be differ compared to the others architectures. How about that if we talk about you have a good or the best of a processor, but it want to definitely need to have a high of a power energy. So that is we discussed in the practical class. Please recall back. And what about the memory? So when you share the memory, do you need to have an additional of what we call implementations to manage your memory? Okay, so that is basically about this one. Okay, data center, because data center is I guess the best of example technology which is affected to the changes of the current computer architectures. So what is a data center? Definitely we have a question about this. What is a data center? And I'm going to give it to you this what we call this document in the for your reference in the my time, and you will see this the references for you to see briefly what is a data center. They have talk about this one, and then roughly data center for me is like a headquarters, okay, that have many of the data, and then inside that they definitely required a network of equipments and connecting to the server, and you're going to have that definitely the operation people going to do that. And the data center foundation definitely have a power cooling and OEM and operators. I did mention about this one. Okay, and before, what is the power? Power definitely the energy, because you need to make sure your servers is keep up the performance 24/7, and then you need to have also cooling system and backup for the open equipment manufacturing, and then people were doing that operations. And then most of the powers data centers, they are having using kind of processors, CPUs. We have the GPUs and the ASICs. So, and each of the components, okay, can work independently. Entirely is using the distributions techniques. Definitely is about what we call the networking techniques. So in the networking, you learn about the topology, about the networking. You know that each of building and data center have other data center that connected each other, and then it has a resource management for that. Okay. So yeah, I did mention about this one, and then the most important in the data center is the location to store all this data, and then it must be protected by a good of a security layer. So, but all of this will be managed by special what we call divisions, ASIC. You know what an ASIC, right? Is stand for application specific integrated circuits, which is their most like it's a custom design, and then have a high performance. It's helping for the crypto, computational, for the AI analytics or data analytics, automotive machine learning methods. That's all basically for the current trends of technology. So this is will be asking, in your final exam, but I simplifying everything under this set. So that's why you can see that like question number 3, like question number 4, question number 5, 6, 7, asked about what is implications of computer architecture changes? What will be the challenge of the current of computer architectures, the trend in terms of memory, in terms of processor, in terms of our consumption? And then I also have how to improve. So normally I will ask you what is challenge, what is a problem, what would be the solution for each of that. So if you suggested that, the problem in terms of power energy, so what is the solution? The problem and challenge in the current of computer architectures, which is following the trend in terms of memory capacity. Okay, what is solution? So that will be inside the case study question. And then I have also questions about the data center, because your case study will be talk about data center. So that is what I said just now. Really significant for you to know what is the data center, and then how it's worked. But foundation of data center I already mentioned just now. They have a power consumption, have networking equipments, and then they will have a cooling mechanism. They will have OEM and also operation people, resource management people. And then this is a type of computer architecture that can be used in that certain of what we call distributed of computer architectures, or what kind of multi-core processing can be adapted or can be used for this type of data center. But if you look at to this example of question, okay, question number 8, I only need 2. Maybe I need 3, maybe I need 2, but not more than that, only 2 or 3. I will say that please suggest for this ABC company data center, 2 example of computer architecture suitable for that requirement. Same goes like tutorial 11 question. Okay, suggest what kind of architecture. So you can suggest SMP, you can or clustering computing or grid computing or multi-thread computing. Make sure that you're giving briefly, giving description, what is this, okay, when you suggest. And yeah, question number 10 until the rest also about the data center, so you know how significant the data center there will be in your final exam. So I guess that we can wrap up for that. Please do this homework for you. I have nothing else that can helping you, only this, and I hope that it's possible to capture every single of the gist for the set of set of revisions. I hope that and all the best. So for the computer trends, always take a look upon on what you need to focus, what is the Moore's law said, and then what is the data center features, and then architectures for the data centers, and after that, what is the problem and the solution to solve it. So that is this all kind of things will be in your final exam for the case study in the part B. Okay, so for this set revision, number 3, they are covered for the case study part B in your final exam. So I'm done with the recording. I hope that everybody can take a look on that. And this one I'm going to update after this. And then for marking for in Cosma, we were still waiting for Bravo groups. And once I got that, I wish I can make it by today. Waiting for the lecturers. And yeah, you can take a look and view your career mark later on. All right, I can stop sharing this one, and yeah, I'm going to upload after this. Wait. Oh my God, stop sharing. Okay. And stop recording.